Alrighty, let's do this. Or get started and get far enough along so we can do the homework. It's due on Friday. Starting today, or starting tomorrow, I think, is the learning center. Anika's going to be there in there tomorrow morning. She's got, I'll post the schedule on Canvas later. She's also going to be in the learning center, I think, on Wednesday, Thursday, and Friday afternoons. And she's just sitting there, she's waiting for you to come in there and ask your questions, right? And so that's actually a good place to actually maybe work on your homework, would be in there, because you know that you have help with her right there. And she's worked out all the problems, she has solutions to everything, she'll be able to help you pretty well. That's a really good resource. The university knows this is a difficult class, and in order to support you, they've provided us with this extra resource of having a TA literally just there to help you whenever you want, okay? So start looking at that stuff. Okay, so then we talked, just a little recap of last time. I like to do a little recap, right? Statics, some of the forces equal to 0, some of the moments equal to 0. Now some of the forces equal to mass times acceleration, and some of the moments are not equal to 0. They're other things, especially in 3D, it is the biggest equation you've ever seen, right? The structure of the course, we're gonna do particles, then we'll do kinematics, kinetics, F equals ma, work energy, impulse, momentum, then we'll have a test. Then we'll go to rigid bodies, 2D rigid bodies, then we'll do kinematics, kinetics, F equals ma, work energy, impulse, momentum. We'll do 3D rigid bodies and do the same thing, okay? Except for we'll only, on 3D, we'll just make it to F equals ma. We won't do work energy for 3D stuff, right? That's kind of the structure of the class, right? So right now, we're starting out with kinematics and particles, right? So geometry of motion. These are gonna be cases where we are given the acceleration as a function of time, acceleration a function of position, or acceleration a function of velocity. Later on, we are gonna derive those equations, right? But right now, we're just gonna, given this acceleration, given the acceleration function of velocity, or given the acceleration function of position. That's just a given. And then we're gonna say, well, once we get those, how do we get velocity and how do we get position? So it's gonna go one of two ways. We're gonna give an acceleration and work our way towards displacement, or we're given displacement and work our way back towards acceleration. Those ones are a lot easier when you go that direction, because it's just taking derivatives as opposed to integrals, okay? And so we briefly talked about acceleration function of time, accelerating car, a sprinter, something like that. Constant acceleration would be gravity, right? It's not really constant, but we're gonna pretend it's constant. Anything near the surface of the earth will be close to being constant. Acceleration of function of velocity, things like drag and air resistance, viscous flow, right? Acceleration is a function of position, things that have springs, real gravity, and magnets, okay? So that's what we're gonna do. So what we're gonna do right now is kind of come up with a solution methodology for each one of these things, right? And we're gonna start out with the easiest, which is acceleration function of time, which is what you did in physics, okay? And so let's do that, right? Let's drive these equations that we have down here. All right. So in this case, we're gonna go back to the acceleration of function of time. That is dv dt, right? It's the change in velocity with respect to time. That's we came up with that last time, okay? And so what we do at this point, we're gonna do this quite a bit in this section, is we're gonna put all the t's on one side and all the v's on the other. So we'll just move that dt to the other side. So a of t dt is equal to dv. And you may remember, this is just maybe some review from your calculus. So put the dt on that side. Well, we got the dt on the top and the dv on the top. Now we can integrate. We integrate this side, integrate this side, right? And this is gonna go from T naught to T. This is gonna go on from V naught to V, right? And we can actually carry out the right-hand side. If you carry out that integral, this just becomes V minus V naught. And that's just the right-hand side. The integral of dV is just V minus V naught, okay? And when you get to this point right here, what we solve for is this V. Okay? So now it's just an algebraic expression, and I just solve for that v, which just means I'm going to add v naught to the other side. And then that's where we get this. That's all we did right there. Okay? We just added v naught to this side. So if you're trying to solve these problems, right, we started out with acceleration, and we moved on to velocity. And we did that by taking the first integral of the acceleration, right? And then we just add on the initial velocity. Well, that kind of makes sense. You have acceleration, you just integrate it with respect to time, you just add on to the initial velocity. Start out with some initial velocity. We're just going to find the change of velocity by adding onto the acceleration integral. Okay, same thing we do down here. Now just come down, how do we solve these problems, right? Now we have the velocity as a function of time, right? After we carry out the step above there, we're gonna have velocity as a function of time, and that's just gonna be ds dt, right? The rate of change of position, right? We're just in 1D stuff, remember? We could have made that jump. Same thing that's gonna happen. We're gonna put all the t's on one side, so v of t dt is equal to ds. And then we carry out integrals on both sides. This is gonna go from t naught to t, and this is gonna go from s naught to s. We can carry out the right-hand side. This is gonna be s minus s naught. And again, we're gonna solve for s, because we want s as a function of time, right? You solve for that s, and then just rearrange the equation. This is what we get. Okay. That one's pretty straightforward. That's what you did in physics. Pretty straightforward. Okay. Any questions about that, right? So to get this, right, again, what you're going to have, we'll do some examples here in a little bit. What we're going to have is you're going to be given this acceleration. That'll be an equation, acceleration function of time. Will be an equation, and then to get to velocity, we're just going to integrate that equation that was given to you, and then you add on the initial velocity. Then that will give you velocity as a function of time. Now you'll have that as an equation, and then to get the position, we just integrate that equation that we just solved for right there, and then add on the initial position, and we're done. Okay, pretty straightforward way to solve those problems. Okay, any questions about that one? That's the easiest one. The second easiest one. The easiest one is constant acceleration. Constant acceleration can be thought of just as a subset of acceleration of function of time. It just isn't changing with respect to time. Right, so the same methodology we're going to use here. Right. In this case, though, a of t is just equal to a naught. It's constant, it's not changing. And again, we just set that equal to dv dt, because acceleration is the velocity, is the derivative of the velocity. Put the dt's on one side, a naught dt is equal to dv. Integrate this, t naught to t, v naught to v. Right? And now, though, we can simplify it a little bit more, because I can actually carry out this integral. I can carry out the integral because I know what the equation is, just constant a naught. So I can actually carry out that integral, which will just be a naught times t minus t naught. Right? And on the other side is going to be v minus v naught. And again, what I'm solving for is this v. So once I carry that out, I just solve for v. Right? And you'll have t's on one side, so then that'll be v as a function of time. And that's what this equation is here. Okay. And that one, right, just your common sense would be that. Acceleration is the time rate change of velocity. So I want to know how much velocity is changed. I do acceleration times the change of time. Acceleration times the change of time, that's this component. That'll tell me how much my velocity has changed, and I just add on to it that velocity. Okay? But we got there, with integrals. But really, right, you could kind of piece that together. Okay, same thing happens here. Now we get to now I'm going to have velocity as a function of time. Now I can carry out that integral. So v a function of time is just a naught times t minus t naught. And we'll do the same thing. We'll come over here, say v of t is equal to ds dt, right? Do the same thing, put all the t's on one side, v of t dt is equal to ds. We integrate, right? What goes in for this velocity equation is this. That goes in right there, right? And so if you took the integral of a times t minus t naught, then you'll get a times t minus t naught squared over 2, right? And take the integral, and then you'll have some other components too. This v naught, it'll be v naught times t, right? So this right here is just the integral of this, right? That equation should look familiar to you, right? That is an equation from physics. So now I have my position as a function of time for constant acceleration. Right? Does that look familiar to anybody? Should, right? Should look familiar to you, right? If it doesn't, you might be a little scared, like, oh my God, what do I do, right? But this is just a subset of it. All right, everybody with me, right? So that's constant acceleration. Sometimes, we're gonna get to this a little more advanced maneuver, some more calculus here. Sometimes you may want velocity as a function of position. Right? It might just happen sometimes. Certain problems you're solving, you might want to go that route, okay? And so there's a way of doing that. With constant acceleration, there's like a kind of a shortcut we can do, right? A naught is equal to dv dt. There's also a good point to introduce the chain rule. Okay, so that's it, right? We're just same thing. We're just saying A naught, my acceleration, is the time rate of change of my velocity. Okay, so then what I do at this point, we can do this, right? In math, I could just multiply this by ds over ds, right? You could do that. It's just multiplying by 1, right? ds over ds is just 1. So I'm going to multiply that side ds over ds, right? And I can rearrange this too, right? I could rearrange this. So this can be dv ds dt, right? I just moved this s. I just moved this s over to this side and moved that dt to that side. Okay, and there's a reason we're doing this. So dv ds. What is ds dt? What's ds dt? Velocity, right? That's my velocity. So then I could just do this. And this is going to become velocity. And this is equal to dv ds times the velocity. Right? And what I did right there, this is the chain rule. We're going to use that again in a few minutes. You have to use it to solve these other problems too. Oop. And that was the chain rule. Okay, so let's come back, just kind of rewrite this thing here. A naught is equal to dv ds times velocity. I'm going to put the ds on this side over here. A naught ds is equal to v dv. And we got the ds's and the dv on the top. We just go that. We integrate this from s naught to s, and this from v naught to v. Okay. And if you carried out these integrals, right, considering that a naught is constant, okay, if you carry out that and you solve for v, this is what you get. A lot of dots here. And you get this equation. There are going to be certain problems where you may want to do that. Right? So you kind of skip times out of it at this point, right? We don't really care about time. Now we just have velocity as a function of position. Right? It's kind of a shortcut. Sometimes you may want to do that. Also, it's a good way of introducing this chain rule. In a minute, we're going to have to use the chain rule in more detail, or have to use it to solve these problems. That's kind of just a shortcut. Can you do these problems without going to that? Absolutely. You just have to go through the time domain. You have to it's just a little bit harder to do that in the certain problems. Okay? Everybody with me? Everybody able to read all my stuff and go at a good pace, all this? Getting out the best handwriting, but it works. Okay. All right, so let's do it now, right? How do we solve acceleration as a function of velocity? Right, so when you solve these problems, it's one of the things you're going to have to do is say, what type of problem am I solving? Is this acceleration function of time, is it acceleration function of position, or acceleration function of velocity? And you have to notice that first. Once you notice that, then come to your notes and see how you would go about solving it. Right? Where I see people run into problems this first section is they try doing it with trying to just integrate with respect to time every time, even though there's acceleration function of velocity. You just can't do it. You're going to get the wrong answer if you do that. Okay. So this is acceleration function of velocity. So this one, like I said, a little more complicated. This may be, remember for last time I said, I think immediately we're going to start like deviating from what you did in physics. I think this is right here. I don't think you did acceleration function of velocity in physics. Maybe you did, but I don't think you did. All right? AV is equal to dv dt. Right, so now, you see what I'm saying is I can't just put this dt over on this side and then integrate with respect to time, because when I take that integral, that my acceleration isn't a function of time, it's a function of velocity, right? So you can't take the integral like that, right? So then what I got to do is, well, we just put everything with a v on one side and everything with a t on the other side, right? It turns out there's nothing else with the t, so it's going to be by itself on the left-hand side. So just do that, right? To put all the v's on one side and all the t's on the other side. So dt is equal to that, right? And kind of rewrite this a little bit if you want. You could call this 1 over acceleration function of velocity times dv. And we could do that. I mean, literally, when you get to your equation for acceleration function of velocity, it's going to be something that's given to you, where you just put it on the bottom and integrate it. That's all we do. Right? So this is going to integral. This is an integral. This is going from t naught to t. This is going from v naught to v. Because we're integrating with respect to velocity over there. Okay? And that's it, right? That's all. That's as far as we can get in terms without doing an example. But that's it. That'll give us the... What we're going to do here is we're going to carry out integral and solve for variable v, which gives you v as a function of time. We'll do this as an example so you can see it kind of play out. But literally, you just carry out this integral, and when you carry out this integral on the right-hand side, you're going to have v's and v naughts floating around, right? Because this is when you carry out that integral, and then you do the definite integrals, you put the v's into the place where v's at, and then you carry out it, and you're going to have a bunch of stuff with v's and v naughts and stuff on the right-hand side. On the left-hand side, you're going to have t minus t naught. And then what you do is you just solve for the 1v, not the v naught, you solve for the 1v. You kind of rearrange the equation just algebraically and solve for that v. And so you have v on one side and a bunch of other stuff with t's and v naughts on the other side. There's your equation. That's velocity as a function of time when you do that. Okay? That is what we're going to do there. Okay? When you get done with that, you now have velocity as a function of time. We've already done that one, right? You have velocity as a function of time. To go to position, right? We just integrate that with respect to time, because now everything's in terms of time. So this v of t, okay, same method we did before, is equal to ds dt. V of t dt is equal to ds. We integrate. This is going from t naught to t, s naught to s, right? And when you do that, you get s as a function of time. Cool. Okay. We're almost there. We're almost to doing an example. All right, one more shortcut. We're going to give you another shortcut here. Similar to what we did last time. Uh-oh. Right. Maybe we want velocity as a function of position. Okay, so let's do that quick little shortcut. If we have that here, actually we do an example where we use this later. Acceleration a function of velocity is equal to dv dt. I'm going to use the chain rule again. That's equal to just dv over ds over dt, right? That again is just my velocity, which is equal to dv ds times velocity, right? Put all my ds's on one side. ds is equal to v over acceleration as a function of velocity, dv, right? And then I carry out this integral, s naught to s, this integral, v naught to v, and that would give me v as a function of s. Give myself enough room here. All right, to do that shortcut, once you get to this point, you do the same thing. You carry out integrals and solve for v. All right. That's a little shortcut. There's some cases where you might want to do that. Cool. All right, last one. Acceleration of function of position. Last one. Acceleration of function of position. So we start out with A of S is equal to dv dt. Again, I can't just put the dt on the left-hand side. I got an s floating around, right? I can't just do that. There's no, you can't take that integral, right? So at this point, I'm going to do that chain rule again. You got to get s in there somehow. dv ds, ds dt. That again is just my velocity. This will be dv ds times velocity. Okay, so now I can move that to the other side. So I have a of s ds is equal to v dv. Integrate this side, integrate this side. It's going from s naught to s. It's going to go v naught to v. Right? Again, what I'm after is this velocity. Right? So you carry out that integral and solve for that velocity. And when you do that, you'll get velocity of function of position. You don't get velocity of function of time, you get velocity as a function of position. Right? Because there is no time in this, right? This is just v's and s's that are floating around. So when I carry out this integral on the left-hand side, carry out the integral on the right-hand side, solve for that velocity, there'll be a bunch of s's on one side and the velocity on the other side, and that's your velocity as a function of position. Okay? So again, just beat this horse to death. I had this colleague, instead of saying like beating a dead horse, he'd always mess it up and say beating a horse to death, right? Which is a completely different picture you put it in your head, right? So I will say it. I know I'm saying it wrong. I just think it's funny to say that, but it's not that funny. Be integration. Carry out integration. Solve for velocity. Right? And I give me velocity function of position. So at this point, I have velocity as a function of position, right? So we come down to position, right? Because again, I'm going acceleration, velocity, position, right? Kind of working our way through this thing. So to get to position, right, my velocity ends up being a function of position. That's just going to be equal to ds dt, right? Put all the s's on one side and the t's on the other. So this would be dt is equal to ds over v of s is equal to 1 over v of s ds. Another way to look at that, I'm going to carry this out. Integral from t naught to t s naught to s. Right? And if you carry that out at the end, you will get s as a function of time. Beat this horse to death here one more time. Carry out integration. And solve for s. Right? And then what you'll get out of it is s is a function of time. Okay, done with the boring stuff. Right? But again, it's kind of like try not to be like cookbooks where we just like, oh, this is how, for these problems, they're complicated enough. We are going to do kind of cookbook. We say, what kind of problem is this? Oh, it's this type of problem. I'm going to go look up at my notes and say, this is how we solve this type of problem. Just to kind of keep you on track. You're going to want, every time, you're going to try to take the integral with respect to time, and you can't do that, especially for these later two problems. Okay, here's the first example. A missile is launched at 100 Gs for 3 seconds. Then the rocket undergoes -4g deceleration. Find how long it takes to reach 15 kilometers. Okay? First example. Right? This is a two-part problem, right? He tells us a two-part problem because it talks about first 3 seconds and then afterwards, right? So we're gonna just treat these things as two different problems. First one, what type of problem is this? Acceleration what? Okay. Yeah, yep, kind of. It is acceleration function time, but even simpler than that, it's constant, right? It's constant 100 Gs, right? And then it's a constant -4 Gs, right? But it is acceleration function of time. Right, so we're gonna solve the first one for the first 3 seconds, then we go to the other one. So it's constant acceleration. Okay. Couple notes here. I am incredibly loose with units. I'm just gonna go ahead and just say that right at the beginning. I don't use them. They're overrated. Okay. If you like to use your units, use your units, right? I think that's good practice. Right? I'm a doctor. Keep in mind, I'm a doctor of this, right? So I don't use them. You should use them if you need to use them, right? I'm just always really careful when I go into these things. Being all right, yep, I'm just gonna keep everything in the same units as I go along. I'm gonna pay attention to it. If you can't do that, do the units trick, right? Where you like write the units on every single thing that you put in, and you'll see that they all cross out, and then they end up with the right units at the end. I apologize for it. I find it incredibly boring. It just slows down the speed of things when I'm writing all the units. So just I apologize. Okay, but they are very important, right? Like in this problem, for instance, right? We got G's, right? Which are units, and so we gotta be careful and make sure that things go in the right units, right? And then it's going to be in metric units because these things are in kilometers, right? And so we're going to be careful of that. And so when we put in my G's, I'm going to put those in meters per second squared. When I put in my kilometers, I'm going to put them in meters. So just be really careful of your units as you're going through. And again, I always just do it where I was like, I'm just going to, I know I'm terrible at it. I'm terrible at it. That's the real reason. It's not that it's boring. I'm just terrible at it. I can't slow myself down and do it that way. Okay, so let's do first 3 seconds. But like I said, when you're first learning, right, it actually is a good idea to keep track of units. Okay, let's do the first 3 seconds, right? And we already identified that this is a constant acceleration case, right? So I'm gonna cheat a little bit because I have an iPad and I know that I'm gonna go to velocity and then to position. Well, up here, I had those equations, so I'm gonna go up and grab them. Grab these two. Can I do this? I'm gonna go down here. Because I can, because I got an iPad. I'll be able to do that, right? So to go to velocity, right? Since I noticed that this was constant acceleration problem, right? I have my acceleration at function time, and it tells me what A naught is. It's 100 Gs, right? And then I'm just gonna solve for that velocity as a function time, and then I'm gonna find out where my position is right afterwards, okay? So you could real quickly write those down. So what this looks like, I can now start plugging values in, right? So this is 100 Gs, right? So 100 Gs, but in order to get it into meters per second squared, I got to multiply by 9.81. Right? So there's in meters per second squared. My 100 Gs times 9.81 gets me into meters per second squared. Okay. And then I'm going to multiply that by t minus t naught, and t naught in this case is 0. All right, so there's my velocity as a function of time equation, right? And so if I want the velocity when I hit 3 seconds, I just plug in 3 seconds into that equation, and I would get this equal to 2943 meters per second. Like I said, I find units to be incredibly boring, but at the end, I always make sure I write my units on what it would turn out, right? But like if you were trying to units, you know what I'm talking about, right? Right here, I would say this is 100 Gs. And then right next to it, I would say that 9.81 is 9.81 meters per second per G. And then the G's cancel out, so I got a meters per second squared, and then T is in seconds. And so then I end up with meters per second squared times seconds, I get meters per second, right? So your units will work out as you go along, okay? And I need to know what my velocity is when I hit the 3 seconds, right? I also need to know what my velocity equation is. My velocity equation is what I just wrote down. It's this right here, okay? Because I'm gonna have to take an integral of it at some point. Okay, so we come down to this. So now I've got my velocity at t equals 3 seconds. Well, how far have we gone in the first 3 seconds? So now we'll come down to my equation for my position as a function of time, okay? And so in this problem right here, I can cross out some of these things, right? I'm starting out at 0 displacement, right? So my S naught is 0 in this case, okay? I also am starting out with 0 velocity at the beginning, right? Starting out 0, right? It's just launching, it's going 100 Gs. So right at the very beginning, it's 0. So V naught here is 0, right? So both of those things are 0. So all I have left is this A naught times T minus T squared, T naught squared over 2. So that's all I have. So then this is just gonna become, this is equal to, right? Again, 100 Gs times 9.81 to get it in meters per second squared. My T naught is 0, right? In this case, my T naught is 0. So this is just going to be multiplied by T squared, right, over 2, right? So that is what my S is as a function of time, right? And what I want is S of T equal to 3 seconds. I want how far it went in that first 3 seconds. I just put in a 3 for my T up there, and I'll get 4,414.5 meters. Okay, so now I know what my velocity is after the first 3 seconds, and then I know what my position is after the first 3 seconds. Okay, so when we switch over to the other part of the problem, right, where we have the deceleration, we're going to have initial velocity and we're going to have an initial position when we're in that section, right? My initial velocity and my initial position will be these two, right? Because starting of the next one, that's how fast it's going when it's starting to decelerate, okay? So the same thing here. This is let's say deceleration. Okay, the deceleration, right? This is negative 4 Gs. A naught is equal to negative 4 Gs. Okay, same equations. Copy them down again because I can. Okay, let's plug in my variables here. This is going to be now negative 4 times 9.81. That's gravity. Times T. Now my T naught is not 0. It's 3 seconds. Right? You could do it as if it's 0, but just know that there's also a 3 seconds that's added on top. It's usually easier just to put it here. 9.81 times T minus 3, because that's my T naught, plus V naught. My V naught is my V from up above, which is 2943. Okay. And so what this is right here is velocity as a function of time. It doesn't ask us anything with velocity, but I need to know what my velocity is as a function of time. Okay, now we come down to the next one. Right, same deal. Just plug in all of our known variables, which you know everything at this point. Negative 4 times 9.81 times T minus 3 seconds squared divided by 2. Right? Plus V naught. I need to know what my V naught is from the previous problem there. 2943. Because again, now it has an initial velocity. T minus 3. And then plus my S naught from the previous part of the problem, which is 4414.5. Right? There's my acceleration as a function of time. I'm trying to figure out how many seconds it takes me to get to 15 kilometers. So what do I do at this point? There's my, what's that?
Solve for T.
Yeah, for but what? But solve for T, but what? By setting what equal to what?
Use stats. equal to 15
Yes,
kilometers?
yes, right? And this is where you gotta be careful. This is where the units come back in, right? You wanna write just this equal to 15, but you can't because it's in kilometers, so you have to put 15,000. Ooh, not the one extra zero. 15,000 kilometers, 15,000 meters. Again, right? If you were keeping track of units like you're supposed to be doing, then you would catch that. But just be really careful of that, right? I'm putting everything in terms of meters per second squared and seconds, and that needs to go in terms of meters. So you're right. I have to set that equal to it, and at this point, I would solve for the time, right? What's the easiest way to solve for that time? Don't say the quadratic equation. Say your calculator. Use your freaking calculator, right? Don't say the quadratic equation. Use the calculator. I am a huge proponent of using your calculator. When you get to stuff like this, plug that shit in your calculator, right? Absolutely. Can you go from right here to the answer? Absolutely. I don't care. Go right to it, right? What's the best calculator? I personally think a TI-89 is the best calculator. Or a TI, what are they, Inspires? Inspire, anybody got Inspire? Nobody got an Inspire? There we go. It's nice, isn't it?
No idea how to use it.
You don't. YouTube it. You can YouTube it and see what it is. It is a really cool tool. TI-89 as well. I swear to God, one of the best purchases I ever made when I was in college was getting a TI-89, right? And I swear by it, right? If you can't afford one, steal one. or ask one for your birthday or Christmas or something. Try to get a TI-89 or I'm serious. It will make a huge difference in your life. Anybody made a switch from an 83 to an 89 or an 84, 89? What do you think? To the Inspire. It's worth it, is it not?
It's crazy.
It's crazy.
Yeah, that's Python.
Yeah, it does all sorts of stuff. It makes your life a lot easier, right? You're over in your math class, right? They don't let you use a calculator a lot of times. But when you're doing engineering stuff, we encourage, it's a tool. You should use it. It's awesome. You can use it on the test. It helps you get the right answers, right? It saves you time. Like instead of me trying to remember and trying to solve this thing algebraically and working out all the details, I literally, in the TI-89, I put it in there just like this, and I say solve for T, and then it pops out an answer, just like within seconds. And then with the TI-89 too, you could see the equation the way you put it in. You could see if you made any errors, and then it shows you the answer afterwards. It's magnificent. I really, I've tried making this that required for this class as a TI-89 or an Inspire, but they won't let me do that. They say you guys are too poor. We have you buy enough stuff. But really, you should really consider. You really should, because here on out, the rest of your college career, you can use it. You can use it, and you might as well use it. Okay, that's my speech. I really think I should buy some stock in TI. But the only thing that I have a problem with the Texas Instruments is the fact that the TI-89 that I use in college is exactly the same as the TI-89 that you would use here, which is like, right, your phones, obviously. Cell phones, when I was in college, were these big-ass things that were attached to your car. They're huge, and right? But we had them. We had them in college, but they were big and giant, right? But then the calculator technology is not kept up, with the exception of the Inspire. The Inspire's in color, and it has like a lithium-ion battery and stuff, right? I'm serious. You will not regret that purchase if you go that route. Right? So I plugged that shit in my calculator, right? And this is 6.68 seconds. Okay. If you didn't could you solve this problem and then just say this was 0 there? You could solve it if that was 0, and your answer there would be 3.38 seconds. And so if you were looking for the total amount of time, you do the 3.38 seconds plus the 3 seconds that already happened to the point where you hit that. But if you put in the T minus 3 there, it'll give you the total time as if from the initial launch. So in 6.68 seconds, this rocket will have gone 15 kilometers, right? Cool. Okay, let's do the next one. Okay, so the mass is released from rest. The spring is unstretched. What did I miss? Something from here. Oh, that's what happened. Something happened here. Oh, that's what happened. I don't know why those are behind it. Okay. All right. So this is going to be, right, this is mass is released from rest, the spring is unstretched, and they tell us the acceleration equation, right? This would be a perfect example. Like we'll do a very similar problem later on when we start kinetics. But in this case, they tell us what this acceleration equation is. But later on, a little foreshadowing, we're going to derive that, right? So this is a spring sitting here. I'm going to have, right, a force of gravity pulling down this direction. I'm going to have the spring pulling up this direction. I sum those forces. I set them equal to mass times acceleration. And then that's where this equation came from, right? And so we're going to come back to this one later. But right now, they just tell us A is a function of position, okay? The thing that's a little bit confusing about this, just to make things a little more complicated, right? What will this thing do if I released it, right? So it's unstretched. If it's unstretched and I let go of it, what does it do? It oscillates, right? This thing goes down, right? This thing goes down, and then at some point it goes back up, and then back down, and then back up, right? So this is actually a vibration type problem, but we can actually solve for the peaks in here as we go along. But really what this thing is going to do is start out with 0 position, and then it's just going to go like this, right? And it's actually going to be a sine wave is what it oscillates at. When you go on, those of you that go on into mechanical engineering, you'll do vibrations, and you'll solve problems like this in vibrations. But this is really a vibration problem where it oscillates. But I can figure out the maxes. I can figure out, what the max displacement that it gets to, right? And so that's what we're going to do. So this is acceleration, a function of position, right? And so then how far does the mass fall, and what is its max velocity? So then at this point, we're like, oh, this is acceleration, a function of position, right? I can't just integrate with respect to time. I have to do some other stuff. So you look back at your cookbook and you see, what do I do with these ones, right? And so I'm going to dive in what we talked about doing last time, right? This is the last one we covered. Acceleration, a function of position, is dv dt. We have to use the chain rule. We got to get some s's in there. So this is going to be dv, ds, ds, dt. Right? This is just velocity. So this is going to be dv, ds times v. Right? And I put all my v's on one side, my s's on the other. So a of s ds is equal to v dv. Right? And so now they told me what my acceleration is as a function of time, so or a function of position. So I take my a of s, which is right here, right? And I take that whole thing and I put it right here, where a of s is. Okay? This is going to be 32.2 minus 50s ds. And I'm going to integrate that from 0 position to another position, s, we call it s, and that's going to be equal to the integral of v dv. This is going to go from 0 velocity to v. Technically, by the way, right, if you're paying attention, if you can't, I'm just have to mention it, like theoretically, I'm breaking a rule. I can't have that s, and I can't have my definite integral, and s is a variable. You have to have a dummy variable. You may remember that you have to do dummy variables, but I cheat, and I'm just going to go right to the, I could go right to the s. If you tried putting this in your calculator and said carry this out, it'll say you can't do it because that's an s and that's an s, and you can't do it that way. But you kind of can, right? We can. So that's what I'm doing, just to simplify. Kind of shorthand of writing these things. Okay, and so I carry out both. So at this point, I carry out the integral on this side, and I carry out the integral on this side, right? And so this will just be 32.2 s minus 50 s squared over 2, right? And you can, how can you do that integral? Well, you can, you remember how to do that, right? This, have to add an s onto that one, and then this would be squared over 2. So when we take the derivative, they go around. Or put it in TI-89 and go, boop, 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 and the out pops the answer, right? That's how I recommend doing it. That's how I do my calculus these days. I will say I rely on my calculator a little bit too much. That's a true story. Like 7 plus 5. Fuck. Let's do it. Right? Otherwise in my head I'm like 7 plus 5. Well, I know 3 gets me to 10. And so then then I got 2 left over. That's 12. Or plug it into the calculator. Okay, so there it is. So I carried out both integrals, right? And I get that. And this is what I'm talking about. If I, at this point, right? Where I said, this is what I keep saying when I was beating the horse to death, right? I was saying, do this integral, solve for v. Well, now I have it, right? I did the integral, I did this integral, and now I just solve for v, right? So there's my v over there. Now it's just algebra, and I solve for that v, right? And so if you carry that, right? Velocity is a function of position. How did I solve for that v? I literally put it in my calculator, right? It's not hard, but there's just a couple steps, but it might as well to put it in the calculator. Boop, left hand, solve is the solve, v squared over 2, and then boop, and then that's what it says, right? I mean, obviously this is an easy one. You could do that one on your own, but that, right? Square root of 2 times 32.2 s minus 50s squared over 2, right? So that is my velocity as a function of position, okay? Now, if I'm asking for the maximum displacement, what will the velocity be when my displacement is the max? 0, right? Because it's velocity's moving this way, and then it hits, and then it's going to turn around and go the other direction. So right at this peak, right? It's kind of weird. We have s going down, positive down. So right at that peak, it's going to have 0 velocity. So to find what my max position is I set this equal to 0, right? And I solve for s. Right now here, right? Yeah, put that shit in your calculator, right? I literally put this equation and I say, solve for s, right? And it comes out and it says, here you go. Here you go, I got it for you. I got it taken care of. S is equal to 1.288 feet, right? My calculator told me that. All right, might as well put it max x, or max velocity, max s, when, right? That's why I set it equal to 0, right? And that told me what my max position is. Okay. All right, last part. Got 3 minutes here. Wants the max velocity. When's my max velocity going to be equal? Or where am I going to get that? My max velocity. And then the acceleration was 0, right? Because it's going to be accelerating in one direction, and then when it starts accelerating the other direction is when my velocity is going to be the most, right? So it's accelerating down, and then as soon as it starts accelerating back the other direction, that's when it's going to happen. So right when acceleration is equal to 0 is when I'm going to get my max velocity. So I go back here. I actually have an acceleration of function of position, right? I know what that's they gave it to us right at the beginning, right? It's 32.2 minus 50s is equal to 0. Right? I can solve for that s right there. My s is equal to 0.644 feet. Right? That's not what they asked us for. They asked what the velocity was, the max velocity. So then I come back and I do velocity function of s equal to 0.644. Right? And that equation, right? This equation I'm talking about is this one right here. Right? So I put in s equal to 0.644 into this equation right here. I'll make note of that right here. Right? And what you get when you just carry out that equation is 4.55 feet per second. Yeah. Okay. Cool. Right. And again, this is just at that instance, just for the first oscillation is when we get that. Right. If you were to plot that velocity as a function of position, and plot that, you would get this going along. Okay, and then next time we'll do this other example. This is going to be acceleration of function of velocity. We haven't done one of those yet. We'll do acceleration of function of velocity. And then that's it. Then we'll go into curved motion. We're all doing 1D stuff at this point, right? Everything's just traveling in one direction. Now we'll start talking about the X and the Y direction, which is just multiple 1D problems is all they end up being. Cool? Break.